Let's start doing the review for the infinite series portion of calculus. First question deals with the integral test. And integral test is a way to see whether a given series converges or not by figuring out the corresponding integral. So you just change all the n into x. And the integration should be same as where the series is done. The series goes from 2 to infinity, so I'm integrating from 2 to infinity. And then I do this integral. If it gives me a finite value, then this series will converge. If it doesn't, then this series will diverge. Okay, now I think this one looks like a question for a u substitution because log of x is a nested function. So du is equal to 1 over x dx, and therefore dx, if you solve this equation for dx, you get x times du. Also, when x is 2, u value will be ln of 2. And when x is infinity, u should still be infinity. Okay. We have x here. Ln of x is now replaced by u. And then dx is x times du. And thankfully, these two x's cancel away, just giving us integral from log 2 to infinity. And 1 over u cubed can be thought as u to the negative 3 du. So now we can integrate using the power rule, which says add 1 to negative 3, which is negative 2, put the reciprocal in front, then you plug in infinity and log of 2, and this is like 1 over 2u squared, and that's where infinity and log of 2 is going in, and that gives you 1 over 2 infinity squared. Well, that's still going to be infinity, so this part will give us 0. Minus negative of 1 over 2 times ln of 2 squared. This will be 0 because it's 1 over infinity, and negative negative is plus, and therefore the integral value is 1 over 2 times log 2 squared, which is a finite value. So by integral test, this series n equals to 2 to infinity of 1 over x times, no, n times ln of n cubed converges. So that's your conclusion. Now, a common misconception is that some people think that this integral value, 1 over 2 ln of 2 squared, is the summation, and that's not true. It's somewhat related. It's I think some modification of this summation, probably from 3 to infinity, that would be bigger, actually less than this integral value. And since this is a positive sum which has an upper bound of this value, that's why this has to converge. So that's how integral test really works. Okay, so all I'm trying to say is that this integral value serves no other purpose than to show whether the original series converges or diverges. The actual value really doesn't say anything about the summation itself. Let's move on to the next question. Here we have to write down the integral 1 through infinity of n over square root of n squared plus 1 dn. Okay, well, some people just write down n rather than x. That's still fine too. For these type of integrals, I think often the u substitution to denote the entire n square root of n squared plus 1, the entire denominator, is actually the one that's preferred. Okay, so and another tip is, when you try to differentiate square roots, it's hard to differentiate, right? So when you do these kind of u substitutions, it's easier if you square both sides and then differentiate as it is. So the left side, u squared differentiates to 2u when differentiated by u. The right side will be 2 times n, and when differentiated by n. Okay, and then you solve this for dn. dn is 2u du divided by 2n, so 2 and 2 cancel, so it's u over n du. Okay, when n is equal to 1, u would be square root of 2. When n is infinity, u will be infinity. And then finally, there's this n. Oh, let's just leave n there, see if it disappears. This entire thing, we decide to call it as u. And since dn is u over n du, now we replace dn by u over n du, and now you see why taking the square root of n squared plus 1 is a good idea, because it just makes the integration really easy. So that just gives us square root of 2 to infinity of 1 du, which is u integrated from 2 to infinity, which gives you infinity minus square root of 2. That's still infinity, which means that the original series diverges by integral test. So that means sigma n from 1 through infinity of n over square root of n squared plus 1 diverges by integral test. Okay, last question. We have the integral 1 through infinity of 1 over square root of n plus 1 dn. And the square root is 1/2 power, and since it's in the denominator, we can rewrite this as n plus 1 to the negative 1/2 power. That's easily integrated by putting the power rule, which says you add 1 to the power. 1 plus negative 1/2 is positive 1/2, and you put the reciprocal in front, which is 2 over 1, and you plug in infinity on 1. So that gives you 2 times square root of infinity plus 1, and minus 2 times square root of 1 plus 1, when these two are put in. And that's just infinity minus 2 right equal 2, which is infinity, and thus by integral test, this sigma n from 1 through infinity, 1 over square root of n plus 1 diverges. Okay. Now use a limit comparison test or comparison test. I think usually we call this direct comparison test. Use either limit comparison test or direct comparison test to determine the convergence or divergence of the series. The first thing, 3n minus 2 over n squared plus 5. Now for these, first thing that you have to know is that limit comparison test is usually easier to use than direct comparison test, because direct comparison test requires the use of inequalities, and often inequalities are not easy to handle. It requires a lot of thinking to use inequalities. So if possible, try to use inequalities and use a limit comparison test. And when you try to use the limit comparison test, it's important that you can find out what this series compares to. So you have this first question, this series here. What does this compare to? Well, what you need to think about is the behavior of this series when n is really, really big. When n is a really large number, then the dominant term on the top is like 3n. The dominant term on the bottom is like 3n squared. So just n squared. Just n squared. So you can see that this value, when n is really large, will be very similar to this value. But what is this one? This is like 3 times 1 over n. And 1 over n is what we call either the P series with P equal to 1, or another way to say this, it's a harmonic series. So we all know that harmonic series diverges, or P series diverges when this P value is 1 right here. So because of that, we should compare this series with 1 over n. This process must be done even if you see solutions in other places or books. They really don't explain this part to you. That's why this limit comparison test looks hard. But if you can figure this out, then the rest is very easy, because limit comparison test always does the following. Take that series that you're given, 3n minus 2 over n squared plus 5, that series that you're given, and then divide by what you want to compare with, which is 1 over n. And then you take limit n to infinity. And this series only works if you can show that this is a finite value which is non-zero. If you get 0 or infinity or it does not exist, then limit comparison test cannot be used, and you have to figure out something better to compare with, or if it looks impossible, then you have to use direct comparison. Okay, so we have complex fractions. Complex fractions, you multiply the inner and the outer, and the outer gets on top, so it's like n times 3n minus 2 goes on top, and then in the bottom, n squared plus 5 times 1 goes on the bottom, and you send n to infinity, which is like 3n squared minus 2n over n squared plus 5. But then the dominant terms on the top and bottom are 3n squared and n squared, so that's just like 3n squared divided by n squared, which is just 3. And indeed, this is not equal to 0. By the way, sorry, I should have mentioned this summation 1 over n diverges by p-test with p equal to 1. This value is p, and that's 1. So when we compare this series with this series, these two sequences, then when you get a non-zero number, that means that whenever this converges, the comparing series converges, this one also converges. If this diverges, then this one should diverge. So what we say finally is that thus, by limit comparison test, summation n from 1 through infinity of 3n minus 2 over n squared plus 5 diverges, because it's comparable to another series which diverges. That's why. Okay, that took a while, but the rest will probably be easier now. So we have question B, n squared plus 1 over 4n to the 5th plus 3. They'll be like n squared over 4n to the 5th when n is really large, which is like 1/4 times, if n squared cancels with this 1, then n cubed is left, so it's like 1 over n cubed. So this 1 over n cubed is the one that we want to compare it with. So we start by mentioning that n equals to 1 through infinity of 1 over n cubed converges by p-test, where p is equal to 3, and whenever this p value is bigger than 1, see, this is your p value, and if that's bigger than 1, you can say by the p-test it converges. Then we take the limit. It's a limit comparison test after all, so we take the limit of the ratios of the two. So we chose this one to compare with this one. So we take an is the given series, and over bn is the series that we're comparing with, and hopefully this goes to a non-zero value. If it does, then we're good. Okay, so we multiply the inside, which gives you the denominator, and this times that gives you the numerator. Limit n going to infinity. That's n to the 5th plus n cubed over 4n to the 5th plus 3. And once again, we see that the dominant terms are n to the 5th and 4 times n to the 5th, so it's 1 over 4, which is not equal to 0. And therefore, we can say that sorry, there was a technical problem. So we have 1/4. That means by limit comparison test, we know that sigma of n from 1 through infinity of n squared plus 1 over 4n to the 5 plus 3 converges. Okay, next one. This one, 2 plus sine n over n cubed minus 2. Now this is not so easy to figure out what to do, because sine n is some unknown value, sine of 1, sine of 2, sine of 3. I have no idea what those values are. I do know that sine can never be bigger than 1 or less than -1. So this is something that's between 1 and -1. So overall, this should be between 1 to 3, because 2 plus -1 will be 1, and 2 plus 1 would be 3. So I know that 2 plus sine n would be between 1 to 3. That I know. Okay, so what can I say? N cubed minus 2. So the trouble with this is I'm not so sure what I should compare this with. I mean, it looks like 1 over n cubed, and when you divide, then and take the limit to try to do the limit comparison test, then this annoying sine n is going to ruin everything. It's going to make the limit of the ratio to not exist. So this is a situation where you need to use the direct comparison test rather than limit comparison test. Now, to do the direct comparison test, unfortunately, you have to figure out before you do the direct comparison test which side you want to argue for. Do you want to say this diverges, or do you want to say this converges? If you choose the wrong answer before applying the direct comparison test, then you might end up doing all the work for no result at all. So you have to kind of use some heuristics to figure out what it does. Well, I mean, as I said, this is like 1 over n cubed, so this divided by n cubed minus 2, this thing here would be like n cubed minus 2, n cubed minus 2, and see, these are both series where if you add these will also converge. These will be finite values. So since they both give you some finite values, I have a hunch that this thing in between should give me a finite value. Now, once you decide that I'm going to argue for this being finite, then the strategy would be to bound this summation above by something that's slightly higher, which converges. Okay. If I thought that this would be infinite, if the summation of this sequence would be infinite, then I would try to bound this from below by something that diverges. So that's the main difference. Okay, so let's argue for this. Since we already have this inequality here, we can say that 2 plus sine of n over n cubed minus 2 is less or equal to 3 over n cubed minus 2, because sine n can be at most 1, and 1 plus 2 is 3. So definitely this side is bigger. And then if I increase the denominator to just give me 1 over n cubed, then this one is That's not good. So if I increase the denominator, the overall, it becomes smaller. So actually, this is the opposite of what I wanted. Well, in that case, what you do is just do something like this. N cubed minus 2 would be greater or equal to n cubed minus half of n cubed, right? Well, you have to be careful here. I think n has to be at least 2 or more for this to be true, because if n is 1, then this inequality doesn't work, because when n is 1, n cubed minus a half is definitely bigger than n cubed minus 2. But starting from 2, this will be n cubed minus 2, and this will be n cubed minus 4, so you see that this is definitely smaller. Now, why is this important? It's important because this is 1/2 of n cubed, and therefore I can now write down this right side as 3 over n cubed minus 2 is less or equal to 3 over 1/2 n cubed. And that is something that's really easy to handle, because this is same as 6 over n cubed. By multiplying 2 top and bottom, you multiply 2 top and bottom, this 1/2 cancels, so 3 over 1/2 n cubed is same as 6 over n cubed, and this is 6 times 1 over n cubed, which is a p-series which converges. So we have to work hard to get an inequality, and as you can see here, direct comparison test is not very pleasant to use. You have to deal with inequalities. All right. Now I think this is all messy, so let's try to do this all over again. So first we start by saying that n cubed minus 2 is less or equals to n cubed minus 1/2 n cubed, which is same as 1/2 n cubed, if n is 2 or greater. And often when you write things, it's the logic flows better if you write down the last thing first. So since we kind of use this in somewhere in the middle, you want to mention this first. And the trouble with that is, although that's easier to follow the logic, for the person who's trying to see how he got the answer, it's really hard to figure out why he's starting from this thing, right, out of nowhere. But that's math. Sometimes in math, when you read something and you don't know why he's starting from there, you have to read between the lines and see where his intention was. Okay, so we start from this, and then we say 2 plus sine of n over n cubed minus 2 is definitely less or equal to 3 over n cubed minus 2, because sine is, so since sine n is less than 1, so we know that's true. And then from above, since n cubed minus 2 is greater or equal to 1/2 n cubed, and when you decrease the denominator, you end up with overall increase in the fraction. If you decrease the denominator, the overall value will be bigger. And then you can simplify this by multiplying 2 top and bottom to give you 6 over n cubed. And this is a good thing, because sigma n from 1 through infinity, 6 over n cubed is 6 times sigma n from 1 through infinity. 1 over n cubed is a p-series with p equals to 3 greater than 1, which converges. Okay, and then because sigma n from, well, this is true for n equals 2 and after, so sigma n from 2 to infinity of 2 plus sine n over n cubed minus 2 is now less or equal to 6 times sigma n from 1 through infinity, 1 over n cubed. That means sigma n from 2 to infinity, 2 plus sine n over n cubed minus 2 converges by direct comparison test. And when you prove that a series converges starting from 2 or 3, that's okay, because this series is just different from this by just some finite term. So showing that this converges is enough to show that the original series converges. So that's how you show this thing converges. Okay. Now D, we have cube root of n plus 1. Again, this is a very easy application of the limit comparison test, because the dominant terms are n to the 1/3 and n, so that's like 1 over n to the 2/3, right? Because 1 minus 1/3 is 2/3. And if you have the summation of this is a p series with p equals to 2/3, so it's gonna diverge, and that means this should diverge too. Okay, so let's start with our p series. Sigma n from 1 through infinity of 1 over n 2/3 diverges by p test with p equals to 2/3, and when it's 1 or less, this diverges. Then we can say that the limit n going to infinity of the given series over the 1 over n to 2/3 is equal to limit n going to infinity. We'll rewrite this as n to the 1/3, and the outer goes on the top, so n to the 2/3 times n to the 1/3 goes on the top, and then on the bottom you have n plus 1. And 2/3 plus 1/3 is just 1, so you just have n over n plus 1, limit n going to infinity, which is 1, which is not equal to 0. So by limit comparison test, the series diverges. Okay, that's how you do D. Okay, now let's try E. Sine of 1 over n. Well, so I spoke about how the Fourier series of sine x, which is x minus 1 over 3 factorial x cubed and plus and so on and so on, indicates that when x is really, really small, these values are small, and sine of x is very close to x. So when n is really big, then 1 over n is a really small number, and because of this fact that sine x is very close to x, this will be very close to 1 over n. And since 1 over n diverges, summation of 1 over n diverges, so I know that summation of sine of 1 over n would diverge too, just by using limit comparison test. So let's try that. Sigma of 1 over n, n from 1 through infinity, diverges by p test, p equals to 1, and then limit of n going to infinity of sine of 1 over n divided by 1 over n. Well, I think you probably want to use change of variable, so set x equals to 1 over n, so the top will be sine of x, the bottom will be x. Okay, and then instead of n, we have to say where x goes to. When n is infinity, 1 over infinity is 0, so x will go to 0 plus. But what's sine x over x limit when x is set to 0? We learned in Calculus 1 that this is equal to 1. Or if you forgot that fact, you can just differentiate top and bottom, because this is a 0 over 0 type. So that means we can use L'Hopital's. When you use L'Hopital's, you get cosine x over 1. And when you plug in 0, you get 1 also. So either way, you're going to get 1, which is not 0. That means our limit comparison test succeeded. Now we can conclude that by limit comparison test, sigma of sine of 1 over n, and from 1 through infinity, diverges. Okay, what about this one? 3 over n plus square root of n cubed plus 2. Well, let's see. This is when n is really, really large. 2 is not dominated by n cubed. So n cubed is the dominating term, which is n cubed, and then there's a square root. So it's like n to 3 over 2. Now, n to 3 over 2 is bigger than n to the 1. So among these, this one will dominate this n. So you can see that when n is really large, this will be pretty similar to 3 over n to the 3 over 2. And this is a p-series with p equals to 3 over 2, which means that since it's bigger than 1, this series will converge. So that's what we will do. So sigma n from 1 through infinity, 1 over and 3 over 2 converges by p-test with p equals to 3 over 2, and that's bigger than 1. Whenever that's bigger than 1, it converges. Okay, now limit n going to infinity of 3 over n times n plus n cubed plus 2 over 1 over n 3 over 2 is same as limit n going to infinity of 3 times n 3 over 2 and n plus n3 plus 2 3 over 2, not 3 over 2, sorry, 1/2, square root is 1/2, so 1/2, and since this is n to 3 over 2, these two are comparable, and this is dominated by this term, so you're going to get the limit as 3, which is not equal to 0. Now, if you're unhappy about this way of thinking, then another way to go about showing this would be to apply the L'Hopital's rule. So you differentiate top and bottom, then I guess you want to differentiate twice. Twice would be better. So try to differentiate top and bottom by twice. Apply the L'Hopital's twice, you're going to get the same result with longer work. Okay, so you get a non-zero value. So now we say by limit comparison test, the series converges. Okay, question G. Here, 1 over log of n is nothing that we have seen before, and therefore we really don't have anything to compare with. That's the problem. Now, that's why there's this suggestion. Suggestion says, first prove this by the integral test. And this is an interesting proposition because if you try to test this one by integral test, you're going to be met with the integral that's impossible to solve. You're going to get 1 over log of x dx, and that's an integral where you can't really solve. So rather than suffering with this, we use this integral, and after we show that this converges or diverges, and then we have to figure out how to relate these two. Okay. All right. So we have x ln of x dx. We have u equal to ln of x. That's the requirement for doing this integral here. Du would be 1 over x dx. Multiply the x to the other side, so you have dx equals to x times du. And then when x is 2, 2 goes into x, that gives you u as ln of 2. When x is infinity, u is still infinity. You have 1 over x times u, and then x times du, x cancels, and 1 over u integrates to ln of u. And you're plugging in infinity and log of 2, which when you plug in infinity, it gives you infinity, minus when you plug in log of 2, you get log of 2, which is some finite value. That means this will end up being infinite. Okay, great. So we see that this thing diverges. So I should say, your conclusion. is thus sigma n from 2 to infinity of 1 over n ln of n diverges by integral test. Okay. Now what about this other one? Well, I guess if you're to say this diverges, this one probably diverges too. Why is that? Well, because 1 over log of n is bigger than 1 over n log of n. If you have log of n, and so since log of n is less or equal to n log of n when n is 2 or greater, when n is 2, this will be twice of that. So actually, I think this is true for n3 or after, because log of 2 is a negative number. Sorry. This is true for n2 or greater. Okay, so log of 2 is a positive number, so 2 times log of 2 is definitely bigger than log of 2. So this is true, and thus if you flip both sides, you're going to get the inequalities flipped. The inequality will flip, and then if you say summation, this is going to be true. But what does this mean? This is infinity, and this is bigger than infinity, so this must be infinity too. Okay. So therefore, sigma n from 2 to infinity of 1 over log of n diverges by direct comparison test. Okay, we have a whole lot of questions here. Use the ratio test or root test to determine convergence or divergence of the series. So what's a ratio test? Ratio test does the following. You define an plus 1 over an, and then limit n going to infinity. That value is defined as r, and if this value falls between -1 and 1, I know that this converges. The series that you do converges. So sigma an converges. And if r absolute value is greater than 1, meaning that if r is bigger than 1 or r is less than -1, then we know that sigma an diverges. And the important thing is when r is 1 or -1, then ratio test is not enough. Test doesn't work for this. So that you need to use another test. Use another test. Okay. Now, if you want to use the root test does the following: limit n going to infinity. You take the nth root of the an, and this value is called r in the root test. And let's see. Let me write down. This one is ratio test, and this one here is a root test. Okay. So, and then the remaining is the same. If r is between -1 to 1, it converges. If r is 1 or -1, you have to use something else. And if it's like this, then it diverges. So it's the same conclusion. And the idea of these tests both arise from trying to make sense of the series itself by thinking of them as something similar to a geometric series. That's why we use the same symbol r. See, in geometric series, this all is true, right? The difference is that when you have an honest geometric series, then when r is 1 or -1, the series diverges. So that's the only difference. Now, when you try to use the root test or ratio test, I find ratio test usually the easier one to use. especially when you have a factorial in your question, then it's a good idea to use ratio test. Now, when do you use the root test? Root test is when you have something to the nth power. These will be good ones to use, and even this one. These will be good ones for root test to do. Now this one here, n over 3 to the n, this one is, you can use either. You can use ratio test or root test. They'll both work. So for this one, let me show you how to do it in both ways, and you should decide which one you like better. Okay, the first one, this one has factorials. Okay, so we're going to use ratio test. Let's see how that works. R is equal to limit n going to infinity of an plus 1. See, this one here is your an. That goes in the denominators, 2 to the n over n factorial. And then you have to write something similar, but instead of n, you have to use n plus 1. So instead of n, 2 to the n, you write 2 to the n plus 1. And instead of n factorial, you write n plus 1 factorial. You simplify the complex fraction as a limit n going to infinity. If you multiply the inside, it goes in the denominator, so it's 2 to the n times n plus 1 factorial. If you multiply the outside, that goes in the numerator, so it's n factorial. Okay, now 2 to the n plus 1 divided by 2 to the n, that's easy. The exponents subtract, and you're just left with just 1, 2. But what about n factorial? Well, don't forget what n factorial means. And n factorial means you start from 1, 2, 3, and you go all the way to n. You multiply everything. Now, if this is n factorial, then what does it mean to have n plus 1 factorial? That means 1, 2, 3, you go all the way up till you get to n plus 1. And then you ask, what was here 1 before n plus 1? Well, 1 before n plus 1 is n. So you see that if you write out the n plus 1 factorial, it contains everything that's in n factorial, and then you have one more. Alright, so to explain myself again, this one here, if you simplify, this is simply 2 by itself. And this one here is here, and n plus 1 factorial is here. Now we cross out everything that's common in top and bottom. That gives us the limit n going to infinity of 2 over n plus 1. And that's 2 divided by infinity, which is equal to 0. Okay, that's great because 0 is between -1 and 1. So what does that mean? By ratio test, sigma n from 1 through infinity of 2 to the n over n factorial converges. Alright, next question. Let's try this one here. This one I promise I'm going to show you both. So let's first do the ratio test. So you take limit n going to infinity. You write down the an in the denominator. And on top, you just basically copy this, except that whenever you see an n, you replace by n plus 1. So 3 to the n plus 1. And then we simplify. That's limit n going to infinity of these two multiply to get n times 3 to the n plus 1 in the bottom. And these two multiply to get n plus 1 times 3 to the n. Now that is limit n going to infinity of n plus 1 over n times 3 to the n over 3 to the n plus 1, which is, if you cancel the 3 to the n's, what you'll be left with will be just 1/3. Okay? It's just 3 to the first power, because 3 to the n plus 1 is 3 to the n times 3 to the first power. 3 to the n cancels, and you just have 3 to the first power left. That's why you have this. Now, what is the limit of n plus 1 over n? Well, that's the dominating terms are n and n, so that just gives you 1. So 1/3 is your r value. This is your r value, which actually gives you that 1/3 is between -1 and 1. that means biratio test converges. Okay, this thing converges. Okay, now let me show you how the root test is done. But to do the root test, you need to take the nth root of n3 to the n, which is same as nth root of n over 3 to the nth root. Well, always when you write down nth root, it's better to just put 1 over n. That's easier to handle. And immediately you see that these two cancel and just get 3 down there, and you get n 1 over n. So that's what you have to do. R value will be the limit of n going to infinity of n to the 1 over n over 1/3. Now, how do you get the limit of n to the 1/2? Well, that part is just slightly tricky, but it's not something that you've never seen before. You've seen it before, right? It's e to the ln of n, and then 1 over n is there, so 1 over n can jump over the log, which gives you limit n going to infinity of 1/3 e to the 1 over n times log of n. And since this is infinity over infinity type, we can use the L'Hopital's and differentiate log of n, which is 1 over n, differentiate n, that's 1. That's what you get if you use the L'Hopital. And 1 over n becomes 0 when n is taken to infinity, so you end up with 1/3 e to 0, which gives you 1/3. Okay. Again, for the same reason, since 1/3 is between -1 and 1, converges by root test. Okay, so I guess ratio test is still slightly better. Alright, next. Okay, the root test is best when the entire thing is taken to the nth power, because, I mean, what better can you do than the root test, which just takes the 1 over nth power of your an. So your an, your an is n plus 2 over 3n minus 1 to the nth power. So that's your an. Therefore, r would be limit n going to infinity, an to the 1 over n power, and n times 1 over n just cancels away. So you just have limit n going to infinity, n plus 2 over 3n minus 1, which just gives you 1/3. Well, 1/3 is between -1 and 1, so that means converges by root test. Very simple. Okay. All right. Next, D. Oh, I see a factorial, so definitely ratio test. So r is equal to limit n going to infinity. You have, well, there are some really strange examples where even with n factorial, you still need to use the root test, but we'll never deal with those. Okay, so for our class, at least, whenever you see n factorial, just go for the ratio test. All right, so we have the an, which is n factorial here, and then n times 2 to the n, and the an plus 1 would be just rewrite everything with n plus 1 factorial, n plus 1, 2 to the n plus 1, and then we simplify this by limit n going to infinity of, let's see, n plus 1 factorial times n times 2 to the n over n plus 1 times n factorial, and then 2 to the n plus 1. Okay, so what's that? Well, you see, n plus 1 times n factorial is really n plus 1 factorial, right? Well, why is that? That's because n factorial is multiplication of 1 times 2 times 3 times all the way up to n, and then you're multiplying the next number, which is n plus 1. So if you multiply n plus 1 to n factorial, that's going to be n plus 1 factorial. Well, that's nice because we have n plus 1 factorial up there, so we can cancel these, and therefore what's left is on the top is just n, and this is 2 to the n, and there's this here is 2 to the n times 2 to the first power, so that 2 to the n also cancels with 2 to the n downstairs, and what you are left with is 2. And then you have limit n going to infinity, which is just infinity over 2. And what does that tell us? Well, infinity over 2 is bigger than 1, right? So your r value is bigger than 1. No, infinity over 2 is just infinity. Why am I saying infinity over 2? So infinity is bigger than 1. That means by ratio test, the series converges. Not converges, diverges. That's how you use the ratio test. Okay. Now, slightly challenging here. N plus 2 over n squared. This still has something related to n as the overall power. So in that case, you definitely want to use the root test, which says you take the limit n going to infinity of your an to the 1 over nth power. And that gives you n plus 2 over n, and n squared divided by n gives you n, and you're taking limit n going to infinity. Okay, so when you have a limit where both the exponent and this downstairs, the base is changing, you're taught that you should be using this nice rewriting by introducing e and ln. So it's e and then ln of n plus 2 over n to the nth power. And the reason you do that is because if you make the n jump over, you get something you can handle by using the L'Hopital's rule. Well, it's not quite L'Hopital's rule yet because this is not a fraction. So one way you make this into a fraction is you force it to be fraction by, rather than multiplication by n, you rewrite it as division by 1 over n. You can always do that, right? Multiplication is the same as division by the reciprocal. So you rewrite the multiplication as division, and then once you have a division, then you can use L'Hopital's rule, because L'Hopital's rule always requires fractions. The problem is trying to differentiate 1 over n. That's really not pleasant. So instead of doing that, since you're going to get 1 over n downstairs anyway, try to just set x as 1 over n. In other words, use substitution. Substitution is a great idea when you try to solve limits. Okay, so x is 1 over n. What does that mean? That means that n is also 1 over x. Okay, so what does that mean? That means the limit is now e to the 1 over x. Perfect. N is now 1 over x, so you have a fraction. Log of 1 over x plus 2 over 1 over x. And then you have, instead of n going to infinity, if n goes to infinity, x would be 1 over infinity, which means it's 0. Okay. Let's rewrite just one more time before we apply the L'Hopital's. See, dividing by 1 over x is the same as multiplying by x. Right? So this is same as 1 over x plus 2 times x. Division by 1 over x is same as multiplication by x, and 1 over x times x is 1. And 2 times x is 2x. So that's what you get in the log. Whereas this times 1 over x can be thought as over x, and you have e. So this is same as this limit now, and this is perfect because that's infinity over infinity. No, actually 0 over 0 type. When x is 0, this will be log of 1, which is 0, and when x is 0, you get 0 in the denominator. So Now we can use the L'Hopital's, which says if you differentiate this according to the chain rule, it's 2 over 1 plus 2x, and if you differentiate x, it's just 1, and limit x going to 0. So when you plug in 0, you get e squared. Oh, that was a lot of work, but this is actually much better than trying to do this using ratio test. If you try ratio test, you're going to see that it's not going to give you any result. Alright, so you have e squared. E is like 2.7, so if you square it, it's even going to be bigger, so that's definitely bigger than 1. So what does that mean? That means by root test, the series diverges. Okay, so that's how you handle this. So this is your part E. So E is divergent. Now let's go to F. Again, you have 3n squared, so that probably will work nice with 1 over n. So we're going to take this limit, that's your r, which will give you limit n going to infinity of n minus 1 over n, and then 3n. And from the previous questions, this is very similar. We will just do the change of variable right off the bat. So what was the change of variable? It worked well if we did the 1 over n. That often simplifies having to handle such a thing. So when x is 1 over n, that means n would be 1 over x, and therefore this limit would be limit, let's see, n is 1 over x minus 1 over 1 over x, 3, and n is 1 over x, so it's 3 times 1 over x. And when n goes to infinity, x goes to 0 plus. Okay, and then since 1 over x is same as multiplication by x, this will be same as limit x going to 0 plus 1 over x minus 1 times x, 3 over x, x times 1 over x is 1, x times negative 1 is x. So this is what we're going to be handling. Okay. Now we use the e to the ln trick. E to the ln, 1 minus x, 3 over x tricks, and then that jumps over the log. The exponent inside the log jumps over the log like a frog. Yeah. So you end up with 3 ln of 1 minus x over x e, and that's perfect for L'Hopital because it's 0 over 0 type. When you differentiate the top, it's negative 3 over 1 minus x, just by the chain rule, okay? And then x differentiates to 1, and you're sending x to 0 plus. That gives you e to the negative 3, which is 1 over e to the 3. And e to the 3 is definitely that's something larger than 1. So overall, 1 over e cubed will be less than 1. Since 1 over e cubed is between negative 1 and 1, we know that this series converges by root test. Okay, G, you have a factorial here, so you're going to use the ratio test. Limit, this has to be copied here. Just make a copy. On the top, you just replace n by n plus 1. Well, let's see. What is 2n plus 1 if you replace n by n plus 1? It's this is what you get if you took 2n plus 1 and replaced n by n plus 1. And that's 2n plus 2 plus 1, 2n plus 3. So we'll be writing down 2n plus 3. Now what this means is that if you think about what the number before is, everything is increasing by 2, right? So the one number before 2n plus 3 must have been 2n plus 1. And that's important because that's what's going to determine which one cancels. So everything before here will cancel with this one. Okay. Alright, so let's continue. Limit n going to infinity of the multiplication of the inside is the denominator, 2n plus 1 and then 2n plus 3. And on the top, it's n plus 1 factorial times 1 times 3 times 5 all the way to 2n plus 1. Okay, so as we have seen, these two will cancel each other. So 2n plus 3 will be left. Whereas this is 1 times 2 times until n plus 1. And this is 1 until just n this much. So when you cancel these two, this much, 1 through n, will be canceled away, and you're going to be left with n plus 1 on the top. And since n plus 1 over 2n plus 3 has the limit n over 2n, or 1 half, and since 1 half is between 1 and negative 1, we know that it's convergent by ratio test. Okay, now we have this thing here. They both have powers of n, so I guess we want to use the root test, which is you copy the an and take 1 over nth power. And since 1 over n gets distributed to both top and bottom, you end up with e squared over log of n. 1 over n times n is just log of n. And when n is sent to infinity, log of infinity is infinity. And e squared is just a constant number, which is e squared. So you have a constant divided by infinity, which is 0. And since 0 is between negative 1 and 1, this converges by root test. Okay. Alright, use the alternating series test or absolute convergence test to determine convergence or divergence of the series. Okay. So what is the alternating series test or absolute series test? Well, absolute convergence test says that if you get rid of the part where the sign is changing and just write down the corresponding, so if I take the absolute value, that gives you sigma n from 1 through infinity of 1 over n plus 2 squared. And this thing here is a series which converges because this is comparable to like 1 over n squared, right? And therefore, this is convergent. And if the absolute value version converges, we say the series is absolutely convergent, which means the series itself is convergent. Okay. Okay, so we will do the following. Limit, we're going to use limit comparison test. Oh, before we do that, we have to say sigma 1 over n squared converges by p test. P is 2 and that's greater than 1. Okay, and then we say limit n going to infinity, we compare the two, which is same as limit n going to infinity of n squared divided by n plus 2 squared. Since n dominates 2, so that's almost like n squared over n squared, and that's 1, which is not equal to 0. If it's not equal to 0, that means the limit comparison test works. So hence, sigma n from 1 through infinity of 1 over n plus 2 squared converges by limit comparison test. Now what does that mean? That means the given series, is absolutely convergent. which implies convergence. Okay. Okay. Now let's work on the second one. This, if you take the limit and this one, if you think about this, the absolute version, if you take the absolute value, that means that this part where change of sign is happening, that's ignored. It's just simply 1 over 2n plus 1 factorial sigma n from 1 to infinity. And I mean, since it has a factorial, the ratio test would be the ideal way to do it. But since we've seen so many ratio tests, let me just take a shortcut here. See, if you have 1 over 2n plus 1 factorial, that means 1 times, 2 times, 3 times, 4 times until 2n plus 1. So this would be actually less than 1 over 2n plus 1 times 2n, right? Which is like 1 over 4n squared plus 2n. Okay, that's because the denominator has 2n and 2n minus 1 all the way up to 1. So this always has more terms multiplied than this. And here I'm just taking the last two. Of course, for this to work, I think n has to be 1 or greater. So this always works. And then this would be still less or equal to n squared. Because if you reduce the denominator, see, 4n squared is definitely bigger than n squared. So this denominator is smaller than this other. So overall, if you take the entire thing, this will be bigger. So that means using this, you can simply say this is less or equal to sigma n equals to 1 through infinity 1 over n squared, which is finite, which converges by p-test. And that's a good thing, because now we can use the direct comparison test to conclude sigma n from 1 through infinity of 1 over 2n plus 1 factorial converges. Okay. Yeah, so that saves a little bit of time compared to when you did the ratio. But, I mean, you're probably better off with ratio test. So try to do the ratio test, although I just did the limit comparison test. Okay, so we have this. So that means the series converges absolutely. Okay, so that's the answer. Okay, last question. No, actually there are more questions here. But part C, one thing that you have to know about cosine n pi is that this is same as negative 1 to the nth power. That follows from the graph of cosine. Cosine graph goes like that. And at pi it's negative 1, at 2 pi it's positive 1, 3 pi it's negative 1, and at 4 pi positive 1. So if you look at the integer values times pi, 1 pi, 2 pi, 3 pi, 4 pi, then the cosine goes like negative 1, 1, negative 1, 1, negative 1, 1. So it alternates signs just like negative 1 to the nth power. So this is always true for any integer n. So what we are seeing here really gives you sigma n from 1 through infinity of negative 1 to the nth power over 3n. Now, we know that if you take the absolute value of this, this is not going to converge. So let's see. Sigma n from 1 through infinity, negative 1 over 3n. That just becomes sigma n equals to 1 through infinity, 1 over 3n. Now, if you have something times n or something times n plus another number, those are called harmonic series. If you have a constant over something times n plus c, these are called harmonic series. Harmonic. And harmonic series always diverges. So this diverges because it's a harmonic series. Or you can just say you can use the p-test. P is equal to 1 once you take the 1/3 out. But in most cases, saying harmonic series reduces a lot of work. Okay, so the series does not converge. Does not converge absolutely. But that doesn't mean that it could converge conditionally. So let's see if the alternating series test works. Okay, so what's the premise of alternating series test? Alternating series test, first you have to show that limit n going to infinity of an, which is, this is your an, the one without the sign. This has to be equal to 0, which is obvious, right? 1 over infinity is 0. Second, you have to show that 1 over 3n and 1 over 3n plus 1, when n increases, it's a decreasing function, which is obvious too because the denominator became bigger. So this is your an, this is your an plus 1, and it's a decreasing function. And thus, we can say converges by alternating series test, which means that the series converges conditionally. Okay. All right. Here, this is another series which does not converge absolutely, because if you take the absolute value, this is square root of n plus 1. And this one is like n to the 1/2 over n plus 1. That's like very similar to 1 over n to the 1/2, right? Because this is dominated by n, so it's really n to the 1/2 over n. If you cancel the n to the 1/2 on top, you end up with n to the 1/2 on the bottom. So these two are very similar, and since this limit n going to infinity is limit n going to infinity, when you multiply these two you get n, when you multiply these two you get n plus 1, which is equal to 1, is not equal to 0. And we know that sigma 1 over n to the 1/2 diverges by p-test. P is 1/2, which is less or equal to 1. Okay? So that means sigma of n equals to 1 through infinity square root of n over n plus 1 does not converge by limit comparison test. Okay, that means we have to, we know for sure this is not absolutely convergent. So not abs conv. Okay, we now do the absolute convergent, no, alternating series test. Alternating series test looks at an, which is square root of n over n plus 1, and checks two things. Number one, limit n going to infinity of square root of n over n plus 1, and that's definitely 0 because this is dominated by n, so that's true. Number two, now we have to show that this is a decreasing function, And that's not so apparent, because if you put n plus 1, the numerator increases and the denominator increases. If it's just the denominator increasing, then we can be really sure that the entire thing decreases, but the numerator is increasing too, so it's not so easy to show that an is whether really greater than an plus 1. Okay. And in that case, here's a nice trick to use. Just differentiate it, and if the derivative is less than 0, we know that it's decreasing, right? So just differentiate this. Hopefully you didn't forget the quotient rule. Derivative of the top is 1 over 2 radical n times n plus 1. Minus, when you differentiate n plus 1, it's just 1. And it's when you differentiate and 1 times the other one, square root of n. And then n plus 1 squared. Now this thing here, this is 1/2. If you multiply these two, it's 1/2 of square root of n. So you're going to get negative 1/2 square root of n. And then you're going to get plus 1 over 2 square root of n. Something squared. Okay, I'm running out of space, so excuse me, but I am going to continue over here. So what gives? We know that this is decreasing for this. When n is really large, this becomes 0, and this is some large value. So eventually, this is always bigger than this one. Actually, when n is 1 or greater, if n is greater than 1, then this numerator will be negative. So you're going to get less than 0 for n bigger than 1. And since an prime is less than 0, an is decreasing. Okay, so now you establish that this is indeed true, and therefore the conclusion is that the series converges conditionally by AST. Okay, all right, that was quite challenging. Next, E, we have, well, you know, if you get rid of this, then you have 2n plus 1 over 5n minus 1. But what's that? When n is really large, this is like 2 over 5, isn't it? So definitely when you add 2 over 5, that's not going to be convergent. So we know that this is not absolutely convergent. But if you think about it, this limit itself being something other than 0 actually tells you that the series will not converge. So we just say limit n going to infinity, -1 to the n, 2n plus 1 over 5n minus 1. This is like -1 to the n times 2 over 5. When n is infinity, this is like 2 over 5, and you're sending n to infinity. So that's going to be a limit where it does not exist. And this is what we call the nth term test. So what we're doing is nth term test for divergence. I like to just call it test for divergence for short. Some people just call it nth term test for short. The full terminology is nth term test for divergence. Well, the test for divergence says this diverges. So that was